equations, they're going to give you a logarithm. And I think the key here is you guys are looking at kind of how do I convert back and forth from logarithm to exponential equation, because this conversion is the key piece of solving one of these equations. And I have a b, a y, and an x. And if I have b to the x to y, then I could say 8 to the negative 2 is equal to x plus 1. And here I've set up a single variable equation. Now, this is just simply algebra when we get to this point. You're just using your knowledge of logarithm and conversion, getting this exponential form, and this is just your understanding of algebra here. So, you know x to the negative 2 is really 1 over x squared when we're working with negative exponents. So, and we know 8 squared is 64, so this simply becomes 1 over 64 is equal to x plus 1. Now, there's a couple ways of looking at this. One, I would say, okay, we could subtract 1 from both sides. That's probably easiest to get x by itself, which would mean that you would do 1 over 64 minus, I'm going to convert this minus 1 to 64 over 64, or negative 64 over 64. So I can get a like denominator underneath. And that just simply gives me a negative 63 over 64 is equal to x. And that would be your answer in solving for what x is here. Simple enough. Again, just solving for x. Once you get to here, this is just algebra. So that's one good example there. Here's another. I should have kept that conversion up. I'll put that back up. Again, this is a key piece. The log b y to the x converting to b x to the y. I like to write that down on each question there. So if I'm given log x 0.05 is equal to negative 1/2, and then x to the, now a lot of this, there's some good, has some solid math moves to it. I know x to a 1/2 is square root of x. And I know this is a negative, so this is going to make this a this is going to bring this to the denominator, so the square root of x on the bottom. Can someone tell me what this could be written as a fraction? What this means? What place is this? What place is this? Okay, so I have 5/100ths, right? So I can write this as 1 over 500. Right? If I convert 0.05, it would convert to 1 over 500. Now, a good move here is using an inverse. So I can actually just flip both of these and say square root of x is equal to 500. You can do that. You can do that. That is something you could do in algebra, because if you think about it, the top number is the same, so you're just trying to get this bottom number the same because it has an equal sign. So how can I get this equal to 500? Now, in order to get rid of a square root, the algebra move is to square that entire, because the square root of x squared is just x. And what would be 500 squared? What would I get for that? How many zeros for that? Amy?
Wouldn't it be 5 over 100? Because 1 over 500 would be 0.00.
Say again?
Wouldn't 5 over 100 give you 0.0?
So this should be, okay, you know what, that's a good catch. So I have 5/100ths?
You had
5 100ths?
So yeah, so it'd be 5 over, yeah.
Good catch. I should probably know that. So if we're flipping this, this actually makes this 100 over 5. Like that, right? We flipped it like this. So x equals 100 over 5, which is actually 100 over 5? That I know. Yeah, it's 20. 20? So my x equals 20 here. 5 hundredths. That makes sense. That's a good solid brain fart on my part. I put 1 500th. Yes?
Can't you like also just put the decimal under 1?
So that's one we worked on yesterday. We had 1. So we made it 1 over square root of x is equal to 0.05. And then one other move you could do here is make this square root of x is equal to 1 over 0.05, right? We've taken the inverse, right? Is that what we did? And then if you square both sides, you would end up putting in your calculator 1 divided by 0.05 squared. And what would you get for that? Probably 20, right? I'm assuming that's going to be 20. You can.
Wait, I have a question. Because 100 over 5, like 100 over 5, that's 20, but not squared. Like you have to square.
So this should be. That's another good. So that, well, if you're squaring this, so then you would have 25. 100 squared is going to be 4 zeros. 1, 2, 3, 4. So actually it should be.
So you squared 100?
Yeah, you should have squared. We should have squared the 100, and we should have squared the 5.
That's 4.
That's 2 mistakes on me. 3, I'm going to just have to. Someone can throw a paper ball up front. If I get a 3rd strike, incoming paper ball.
And the 3rd strike be everybody get extra point.
Everybody gets an extra point. So, no. What do we get? 10. This is 10,000.
That's 400.
400. And what do you get when you get 1 divided by point? What's up?
Oh, 1 divided by 0.05.
You get 400, and this also equals 400. Point for Tamani, point for Amy. All right. How about we do it that way?
No.
If you catch me, you get a point. Yeah, I like that.
No.
I like that. Catch me, you get a point.
We know.
Okay.
That's not fair.
Catch me, you get a point. This is, I like this one. Actually, there's one I really, because you actually had to use, let's say, log 3x. Don't worry, I'm not going to forget your extra credit there. So if you're looking at this, and you're saying, okay, how am I going to solve for this? I can't really convert this to my exponential form. Well, key piece here is, well, I know I have to use one of my properties. And what property is associated with subtraction when dealing with logarithms? Quotient. So I can actually expand or contract this logarithm. Yeah, I can, and the reason I could do that is because my bases here are the same. So
What's the difference?
log 3, then you're not able to, because you're not able to expand or contract because you're going to have different bases. It would actually have to be, you'd probably say it's simplified there. And this is going to be x plus 9 over x. Let me just leave this here. And now I have 3 pieces.
Equals what?
I have 3 pieces. I have a b. This here will be my y, and this here will be my x. And now I can set up. I could set up a 3 to the 5th is equal to x plus 9 over x. 3 to the 5th, can I get that? Can I get an assist? Say again?
243.
So we're at 243x is equal to x plus 9. Now if you're subtracting an x from 243, all right, I won't say that. This does not become 243 without the x. It becomes 242x is equal to 9. You have 243 apples, and you're taking one apple, you have this many apples. Divide by 242, x is equal to, can I reduce this? Well, I know 3 goes into 24, okay? And if 3 is not going to go into 2, then I know if 3 can't go into this, then 9 also can't go into this. Like if this was 243, then I say, okay, there's a possibility 9 could go into that, or I can reduce this by 3. But given that 3 doesn't, I know right away, because I know 3 goes into 240, I know right away that's not going to be reduced. Just a little side note here, and this would be your answer here. Now again, the key is contracting this, using a quotient property, setting up your b to the x is equal to y, and solving using algebra.
Okay, can you just explain, just real quick step by step, how you went from that to that?
Here to here? So, that's good, so let's talk about quotient property. So, log b of a minus log b of b is equal to log, let's call this log c a over b. That is your quotient property. If you have two logarithms subtracting from each other, you can divide their two results here. This is one way of contracting them. So I took this first piece, put it on top, divided by the second piece on the bottom.
Bless you.
And if you had something like this, you can, of course, expand back to subtracting the two logarithms. So subtracting and dividing the logarithms are related by the quotient.
So all you did for that is just simplify it into one.
I simplified this into, we could call it one term, one piece, so that I can find something to put for where my y needs to be.
Oh.
Yeah, because otherwise it would be log 3. There's no way for me to really get this one piece on this side so that I could solve for x. I need to, because I don't really have, when I have log b, so I have basically log b to the y minus log b to the y. I have two b's and two y's, but by using quotient property and making it one term, I've been able to just have one b and one y. Browning?
What do you do when the log, there's a log not the
Say again?
same? What do you do when the logs are not the same?
Like the bases are not the same? Well, then you're not, see, that if the base is not the same, then you're not able to expand or contract them. The rule is based on the fact that you have logarithms of the same base. Otherwise, you have a different b for each, so they can't be related. It's like unlike terms. Jeff?
Did you change it to 242 on purpose, or?
Well, we subtracted an x from it. Right? What did I miss there? We gave Jeff an extra point. I subtracted x from both sides.
Yeah, and then it went to 242 and it's.
243 minus x is 242.
243x minus x is
Make it no x.
242x.
When did they make it no
Yeah,
x?
I'll say it.
What?
No, it's
When did they-
Hey,
You pretend it's a 1 and
This is the same thing that happened yesterday to a student. What's 10x minus 8x? What is it? 2x.
Okay, that wasn't the problem though.
So you're saying 10x minus x is 10 now?
But that's different.
How is that different?
It's
This is minus 1x minus 1x
Oh, I forgot it said
is
this.
9x. We are not alone. You are not alone. C is a common mistake with a few C's. Even a good one over here. They thought this needed to be 242. What happened? We've been doing maybe too much advanced math that we forgot the.
So that formula.
We do way too much math before fighting.
That's the quotient property formula?
Yes. This one was a little simpler because you're not working with any real properties here. Again, this is just setting up your 6 to the third is equal to 3x plus 7. So that ends up being a simple, little bit more of a simpler problem because you're just doing like an algebra problem. 6 to the third is 6 to the third.
Can we figure it out?
216.
Okay.
Yeah, I'm letting you figure it out. And then where do I go next?
Okay.
And then that gives me
209, not 269.
x is 69 point. Probably the answer is going to leave it, if your answer choice is going to leave it as a fraction. Most likely.
So every one of these problems you have to convert it?
Convert, yes. Each of these, you're taking the logarithm and you're moving it to exponential form so you can solve for x. Absolutely.
Can you remind me what exponential form is? Or the form?
This is exponential form.
Oh, okay, okay.
And I just threw this one in there. I'm not really sure what it's going to do, but I saw it. Probably should have prepped some of these questions. Maybe I would have known what 5/100 looks like. Got stumped on that one. 36. Ooh, I like this one. 36 to 3/2 is equal to x. So this one is nice because all you're really doing is solving what the left side of this equation is, and you're getting your x. Now this is, who knows how to actually rewrite this? Yeah.
36 to the power and
36 to the third power and the square root of that. So that you can do that many different ways. In a calculator, of caret 3/2 will also work. That you, and you said 216. That was the easier one. It's the layup. That one, good way to finish. If you end up with a log b x plus 7 plus log b, just as a side note, plus log b, let's call it x like this equals a number. What could we use here to contract this? What rule? We use quotient rule that dealt with subtraction. Product rule, which deals with multiplication. So I could have said this is log b x plus 7 times x is equal to that number. Let's just give it a number, say 20. And then you would say, let's give this a number 2. We want the bases to be the same. Let's just work this out. So I would have log 2. You would actually distribute here and say that's x squared plus 7x is equal to 20. And then you have 2 to the 20 is equal to x squared plus 7x. What's 2 to the 20? Is that a huge number? Let's call this 5. Let's make this a smaller number. This way we're not 2 to the 5th would be what? Is that 64?
32.
32? And if you wanted to solve for x here, ooh, I like this one. If I wanted to solve for x here, what's one thing I could do? Review. Yeah, you can use some quadratics, and so you could use your quadratic formula, or you could do what? Solve for your zeros. So I could make this 0 is equal to, that's a +1 for Clea. That's pretty good right there. Plus 7x plus 32. 8 and 4. So you probably would have to use the quadratic formula here, or you could graph this, find your zeros on a graph, and that'll get your answer. Because I don't have 1 and 32, 2 and 16, 4 and 8. No combination of this is going to give me a 7x. But you would solve for your zeros there. You could put that into a calculator or a quad formula, yes.
How did you get 32?
That was from us having 2 to the 5th. 2 to the 5th gave us this.
Oh, you changed it.
So that's good. We got
Can you explain that middle part?
this right here.
Yes.
Yeah, so since we have adding of 2 logarithms with similar bases, we've now brought in the product rule, which tells us log b of a plus log b of c is equal to log b a times c. Which is what we did here. We multiplied the x plus 7 and the x, and got our x squared. Got our x squared plus 7x. X times x, x squared, 7 times x, 7x. So we have our b, we have our y, and we have our x. So I set up 2 to the x, which is 5. Is equal to x squared plus 7x.
So from there you went to exponential formula?
From here we went to exponential form.
Okay.
And then from here we went to, okay, let's see if we can use a quadratic formula. And that's good. We had a student pick up on 2 separate ways of solving for that, which is real solid. So thanks to Amy for teaching Mr. Duffy how to do fractions, and to Monty for teaching me how to square a number, and Kalea for reminding us quadratic formula, which is
It's like 4 A's. Oh, A and square roots on
oh, you got this one.
That's from 10th grade, right? Early
This one, but isn't there like a?
Man, you don't even know.
Is it like this?
Is this first
Is this a minus b or regular b?
It's a negative.
Negative. What's on the bottom? Could have just put that in there from that. That's Ashley and Justin on that one. Josh.
Is that going to be on the final?
That type of question.